Today's experiment is elimination. We are going to get Zaitzev and Hoffman products, and so this is what percent Zaitzev versus what percent Hoffman, also an overall percentage of the reaction. Alright, so we're going to start with our 2-methyl-2-butanol, or the newer UPAC naming, 2-methyl-butan-2-all. The common name is a T-amyl alcohol, where T stands for tertiary. So when we look at our alcohol, it is tertiary. It is connected to a carbon. That carbon does not have any hydrogens on it. It has 2 methyls and an ethyl. And so we're going to get an elimination product, which is going to be an alkene, and it is going to give us 2 products. So the hydrogens on the methyl, there are 6 of those, that's going to give us the same product when it takes off one of those hydrogens and puts a double bond there. The ethyl has 2 hydrogens that will form the double bond. We're going to show that mechanism in a minute. And that's going to be our Zaitzev product. So note that we have 2 methyls, 6 hydrogens that can be removed, and we have an ethyl. And the ethyl, you have to have the adjacent carbon hydrogens, which are only 2 of them. All right, so the first step is the oxygen on the alcohol will take the hydrogen from your sulfuric acid. All right, and now remember, you're going to have to balance every reaction. All right, this is how it's going to be given. You're going to have to balance it. So I'm only going to give the organic product here. And that is your protonated alcohol, which has now a good leaving group. Water is a good leaving group, and you show the arrow of the water leaving, and you have a carbocation. So this is a stable carbocation because it is a tertiary carbocation. That carbon has 3 carbons attached to it, no hydrogens. That is a tertiary carbocation, which is a stable carbocation. It's not going to do any rearrangements. All right, so now we have our bisulfate ion. All right, so that is your sulfuric acid that has been removed one of the hydrogens, and that is going to take a hydrogen. And so in step 3, it's going to take the hydrogen. I'm going to give the major product first. And it takes the hydrogen off of the ethyl. So it takes the adjacent hydrogen. There are 2 of them there. I only wrote in 1. It takes that hydrogen and forms the alkene. And so this is the Zaitzev product. It is the major product in this reaction. I have done this experiment many times, and I ran the GC, and it on average gives an 85% of this product. So 85% is going to be the Zaitzev product, 15% is going to be the Hoffman product. All right, and I will go through why it's called that in a second. So here is still step 3, except this is going to be forming our minor product. And so there are 6 hydrogens on your methyl groups. You have 2 methyl groups, you have 6 hydrogens. I only wrote in 1 of them. Any of those 6 will give the exact same product. All right, and so I show the bisulfate ion taking the hydrogen and forming the alkene. And so this is your minor product. It is the Hoffman product, and that's going to be 15% of our product. And so I got the 85%, 15% by doing a gas chromatograph. And you do the area under the curve. And you get your percentages here. All right, so this is called the Zaitzev product because if you look at the carbon-carbon double bond, the carbon on the left, of the carbon double bond on the left, it is connected to 2 methyls. The one on the right is connected to a methyl and a hydrogen. And so that carbon-carbon double bond is connected to 3 R groups and 1 hydrogen. If you go down here, you see that the carbon-carbon double bond on the left is not connected to any carbons. It is 2 hydrogens there. And then on the right, it's connected to a methyl group and an ethyl group. And so this one has 2 R groups and 2 hydrogens. So more highly substituted is more stable. And so this is the more stable product, and it gives the major product, the Zaitzev product, of 85%. And the Hoffman is less stable, the minor product, at 15%. And so what you're going to do is you're going to have to write the mechanism twice. Step 1 is exactly the same. Step 2 is exactly the same. It is step 3 where you're going to have two different things that you have to write. You have your step 3 for the major product, where it took the hydrogen off of the ethyl, and you have step 3 of the minor product, where it takes the hydrogen off of your methyl group. And so you'll then have to write an overall reaction for the major product and overall reaction for your minor product. When you are getting your theoretical yield, you do not have to do theoretical yield for each one. We're just doing a total theoretical yield. And so if our theoretical yield is 1 gram and we got 0.8 grams, then we have an 80% theoretical yield. Of that 80% yield, the 0.8 grams that we have, 85% of that 0.8 grams is Zaitzev. 15% of that 0.8 grams is the Hoffman product. All right, so also when we are mixing an alcohol and sulfuric acid, these are both polar, and we're going to have one layer. As the reaction proceeds and we form this hydrocarbon, hydrogen and carbon only, which is nonpolar and has a lower density, you're going to see that you're going to have 2 layers forming, and the top layer is going to be your alkene. So try to watch that on the video. Not sure how clear that's going to be on the video. So now we're ready to start doing the experiment. All right, so we're going to do another distillation. So I have the distillation set up right here. All right, and all right, so we have our directions. All right, 15 mils of 6 molar sulfuric acid. I have that here, and it's been in this ice bath for quite a long time, and so it is very cool. And so to this, we're going to slowly pour 10 mils of our 2-methyl-2-butanol that I have in this graduated cylinder here. And so I'm going to, now it's cold, so the reaction is going to happen slowly. All right, and so I'm going to pour it in. All right, and the bottom is still very cold. All right, so try to put this in here, and you can only see one layer. All right, so the reaction is going to go. Now this reaction takes some heat, so as I swirl it, it may generate enough energy here to start separating. Now if it doesn't, we're going to heat it to do our distillation, and then maybe I'll pick up the camera and get it close so that you can see the 2 layers forming. Alright, so right now there's only one layer in here. There's not a top and a bottom layer, it's just the one layer. Alright, so I'm going to hook up my distillation. All the joints are good and tight. Okay, put in the thermometer. All right, make sure the water is flowing. Water is flowing. Slowly but flowing. Again, the water comes in the bottom, out the top, so this is water cooled. And then we have our micro burner. and we will turn on the gas, up, and some gentle heating. All right, so here's where I'm going to try to get us closer and see if we can see this any better. All right. Not sure what the best angle is here, but as we heat it, we should see, so the reaction takes some heat to get it going. And then we should see two layers starting to form. Right now there's just one layer. So as we heat this up, there should be a layer that's going to be forming on top. So you got some milky white. So you got some reaction going on in there. There is visible evidence of a reaction going on in there. Alright, so we are heating it so much that it is actually boiling before we can see our two layers. So we have product being, you can't even hardly see it. The boiling point of these alkenes are very low. Our boiling point, we're at 44 and we are collecting product. Hopefully you can see that dripping in, that we are collecting product. So since the boiling point was so low, we never did get to see the two layers. As the product was being produced at this temperature, it was immediately evaporating and condensing, and now we're collecting it. I was hoping to see more of the two layers, but we could see the milky white but it doesn't take a whole lot of heat because the boiling point of these alkenes are very low. I'm going to put the camera back down. And finish our distillation. So when the temperature shoots up, we know that we are done collecting the alkene. The alkene is very volatile, that's why we have an ice bath to collect it, otherwise it would just evaporate out of there. 40-degree boiling point, so we got, so it's a little higher than it says. So our two products, it says boiling point of the 2-methyl-1-butene is 31.2 degrees Celsius, and the 2-methyl-2-butene boiling point is 38.6. So it is a little higher than that when it's at 44, and it's coming over again. The water is not going to boil until it's at least 100, because you have sulfuric acid in there with it. With the water, the aqueous sulfuric acid is going to have a higher boiling point than 100 degrees. So I'm going to monitor the temperatures, and when this product, which is being formed and immediately boiling, so what's boiling down there is our product is being formed and immediately vaporized, causing the bubbles down there, and then it's coming across, and let's see what and we are, so it's up to 50 degrees for our temperature. Get a little bit of discoloration. If you heat your sulfuric acid too much, you will get some brown, reddish brown. So we're going to collect until we probably, I'm going to say till we hit, it should be 100 before we know we're not bringing over any of our product. And we're going to wash it anyway, so if you bring over a little bit of water, that is not a problem. Or bring over some acid, because we're going to wash it with base. Once that temperature kicks up to, about 100 degrees, we know for sure that we have all of the organic product that we're going to get. And you can also tell the strong hydrogen bonding and surface tension that you have for water. It's gonna, you couldn't even see the vapors coming in being collected when it was the organic layer. When it's the aqueous layer, you're going to see the solvent front, all the bubbles. So we are still at 55 or so degrees. So we're not at, and we are still collecting. Still dripping in at a very nice rate. About a drip a second or so, maybe a drip every 2 seconds. We are still about 57 degrees right now, Celsius. So yeah, when you get this darker color, that means you probably are heating it a little bit too fast. So trying not to heat it way too fast, but it's a little faster than it wants to be heated. I'm just trying to get a nice boil, a constant boil. still coming over, and we are still, now we're reaching, we're up to 60 degrees now. We are going to collect a little bit of the aqueous solution, and that way we know for sure we got all the organic, and that we are done. So I'm not going to stop till it hits 100. It's going up quite a bit. Looks like we're at 80. All right, so it looks like we are now collecting some water, 20, 60. We're still about 80. So I'm trying to see if the drops that are coming over are a different layer than the original drops. Once we have water coming over, it's going to form a second layer as our product, which is fine. That's what I'm looking for in order to stop. But it looks like we are collecting water right now. Okay, yeah, we are collecting water right now. We are at 100 degrees. All right, so we are at 100 degrees at the boiling point. So now we are going to stop the distillation. All right, so now over here we have all of the organic product, and we have some of the water. So some of the water I did distill over to make sure that we had all the organic product. All right, so now we're going to transfer this to a separatory funnel and wash it with 15 mils of 1 molar sodium hydroxide. All right, so again, when you're adding stuff to your separatory funnel, you have to make sure that the lid is closed. The stopcock is closed. You don't want to pour in your product and lose it all. All right, so I'm going to show you this product. All right, so here is our product, and it looks like it is one layer. And you can smell the product, and it definitely smells like a hydrocarbon, a gasoline type smell. Pour that in our separatory funnel. we're going to wash it with 15 mils of 1 molar sodium hydroxide. So I'm going to put it in here. Oh boy. Looks like we had phenolphthalein in there. That's not good. All right, so we'll not worry about that product. We're going to put in 15 mils. Well, maybe that's interesting. All right, so I wasn't really wanting this to have color, but actually it's going to work out nice. We're going to go ahead and add this with the phenolphthalein so you can see that it's forming 2 layers, and so you can see the 2 layers a lot easier than if it were not a color. All right, and so you got your base at the bottom, and we now know it's definitely basic and not acidic. Phenolphthalein and acid would be clear and colorless. All right, and so we're going to wash this, stopcock on, and tilt it up, open the stopcock. And you're going to get a lot of vapors because of this alkene is very volatile. It only has a boiling point of 31 for the minor product and 39 for the major product. All right, and so, all right, so we have that. All right, so we're going to get rid of the aqueous layer, which is on the bottom. All right, so we can put that back in here. Take the lid off the top. I could probably show you what happens if you don't do that as well, but and then get rid of the aqueous layer, keep the organic layer. We're going to get a wash with deionized water. All right, so put in some deionized water. It doesn't matter how much, we just want to make sure that we don't have any excess base. All right. And again, we'll separate that, get rid of the aqueous layer. All right, so now we have our product. Now, your hydrocarbons will dissolve the stopcock grease. And so the reason why you don't want to have a lot of stopcock grease is because you are going to pour this out the top, and you don't want to contaminate it with stopcock grease. And so I'm going to wipe this clean. Make sure there's no excess stopcock grease. All right, and then there is still water in our product, and so we have some anhydrous sodium sulfate. So we have 1 gram in this beaker, and so I'm going to pour this in, and it says to let it dry. Now, let it dry does not mean wait till it evaporates to dryness. It just means that we are getting rid of the water. So you're not going to see anything happen, but any water that has been in there is being sucked in to the sodium sulfate. All right, and so it's a very exothermic reaction. Doesn't feel very warm. And so there wasn't very much water in there, but any water that was in there is now being sucked out by the sodium sulfate. So it's being grabbed by the sodium sulfate, and then that hydrate is still a solid. And so all I'm going to do now is weigh it. And so I have my mass of my Erlenmeyer flask. It is 29.9408 grams. 29.9408 grams. And I'm going to decant, which means that I have a liquid in here and I have a solid in here. Decant means I'm going to pour the liquid in here and the solid is going to stay behind. All right, and so we have given this enough time to find all the water molecules, take them out of our aqueous, or take it all out of the organic solution. And so this is dry. Again, dry means that this organic does not contain any water. All right, and so we are decanting, which means I'm pouring the liquid in here and I'm making sure that all of the solid stays in the beaker. I do not want the solid to come. I only want the liquid. All right, and so the solid is wet. All right, it's wet with water. It's also wet with organic. So by drying it, you're still going to lose some of your product. And that, again, we want purity more than we want percent yield. All right, and so let's see what our flask weighs now. All right, so the flask weighs 34.3027. 34.3027 grams. All right, so we got a little over 4 grams of product. So you will have to calculate the theoretical yield. So we started with the alcohol as a liquid. We started with 10 mils of this liquid. You're going to have to look up the density. You're going to have to look up or calculate from the periodic table the molar mass. You're going to then get moles of that product. And then all of these reactions are 1-to-1. So 1 mole of that would produce 1 mole of product. Get the molar mass of the product. Both products have exactly the same molar mass. All right, and so you're going to get then the theoretical yield of the combination. So this 4+ grams that we got is 85% of the Zaitzev product, 15% of the Hoffman product. I want the overall percent yield. So you have to calculate the total mass of both of those. That's the theoretical yield, and the actual yield is what we have just determined here by taking the mass of the flask with the product minus just the mass of the empty flask. You will also have to show your work. Well, no, you won't. You will not have to show your work for the sulfuric acid because it is not a reactant. If you have sulfuric acid as a reactant, you do not have your overall reaction correct. All right, and so there's only one reactant in this, and so of course it is the limiting reagent, and it is going to give you the calculation for the theoretical yield. That is the end of the elimination experiment.